Great, thanks, Mike. So Mike has given us a really awesome overview of what we plan to do overall in this fairly wide-ranging theme. And now Matthew and I are going to talk a little bit more specifically about what we've done in the past and kind of touch on how that's going to be applicable to these big and complex questions that come up in the Antarctic space. For those of you who don't know me, I'm Kate Helmstedt. I'm a senior lecturer and ARC DECRA fellow at the School of Mathematical Sciences at QUT, and I'm the mentored lead in theme 3 along with Mike. And I'm going to talk about the maths for making difficult conservation decisions slightly less difficult. So when we think about conservation decision science, in all of the problems that we're looking at, we're trying to do kind of the same thing. We're always looking for actions that are going to improve our environment the most from some baseline, given limited resources. And this is a complex decision problem, no matter how we think about it or how we frame it mathematically. For example, improve. What do we actually want out of these systems? What do we want to actually be better at and improve in our environmental systems? And we might get information like this from our understanding of political decisions or from stakeholders. The baseline itself is really complex, so we need some idea of what's happening in our systems if we don't act. And Matthew will speak a little bit more to that, and we've heard a lot about that in previous weeks and themes as well. It's things that we can get from data and models and understanding of the current processes in the ecosystem. The limited resources is a challenge. So what is it that we're actually limited by? What is it that stops us from in our ecosystems of choice? Why can't we just do everything that's the best for every single species? Often it's because we're limited by time or by money or by political capital, but understanding how that's happening or why that's happening or valuing what these things are is a complex part of the problem. But I think mathematically, or the part that I am interested in most mathematically, is the complexity of choosing the actions. So once we've framed the problem, how do we actually make these choices? So I think this is really one of the complex pieces mathematically. And we need specific approaches for different types of questions. There are questions that we know how to answer. We know how to make decisions repeatedly through time. We know how to make choices. We know how to allocate protected areas, as Mike was saying. But every time we address a new problem, we really need to tailor these decision problems for each management context. Just because we know how to do something or have done something well in a different ecosystem doesn't mean that we can just kind of like pick up that approach or those solutions or those algorithms and apply them straight to the Antarctic decision-making space. But the good thing is that we can borrow from many approaches from conservation decisions that we already know how to make. This is a field that, although young, has been around for a while and relies on many, many decades of mathematics in operations research and decision science. And so what we can do is pivot a lot of the things that we know how to do already well into this more complex Antarctic space. One of the things that we know how to do well, and I'll kind of talk a little bit more about today, is the idea of prioritization. And you've, in biodiversity conservation contexts, maybe heard of this as being called triage. In mathematics, we call it the knapsack problem because it's the classical setup or framing mathematically of this problem is about a cat burglar. So a cat burglar goes into your house and they know that they are limited by 2 resources. They only have a certain amount of time that they can spend, and they only have a certain amount of room in their bag or in their knapsack. So what they're doing, what this cat burglar is doing, is sizing up every single thing in your house based on how much value they can get from it, and weighing that up against how much time it takes to take and how much space it takes in that knapsack. This is a really well explored problem mathematically. There are a lot of different ways to frame the problem. There's a lot of different ways to solve the problem, and that's increasing as we get kind of better computers that can solve bigger problems. And we've been borrowing from this knapsack problem for biodiversity conservation for quite a while. And so in conservation, we'll hear prioritization and triage used for things like choosing between species, like choosing between areas, sometimes choosing between projects or choosing between actions. So this is a well-established space. One layer of complexity beyond just prioritizing is the idea of spatial prioritization. And Mike touched on a lot of these ideas in his introduction as well. The reason that the space aspect makes this problem more complex is that, you know, there's different elements and layers to the problem that them being laid out in space affects: the connectivity, the fact it costs different amounts to get to places. And the main approach to spatial prioritization that we see and we're most familiar with is the idea of reserve site selection or protected area planning, as Mike touched on. And we see this working, we've seen implementation of this in the program MARCSAN. So basically this is, and in itself, it's quite a complex idea. We are taking, you know, multiple layers of things like threat maps, of fishing pressure, maybe urbanization. We have conservation features in the landscape we want to conserve, sorry, and we're making some kind of priority decision layer by selecting or not selecting different areas in that landscape. But spatial prioritization, it doesn't just have to be about protected area planning, although we do hear about it in that context a lot. So for example, I'm working as part of my DECRA project on looking at restoration activities in the Great Barrier Reef. And this again is a spatial prioritization problem. We're not just looking at building protected areas, we're looking at where in space we might be able to roll out different restoration activities. And so this adds a little bit of complexity to the problem, where we're now also thinking about things like a layer of feasibility. Where might we be able to do these restoration activities? Where might they be able to have impact? We have different stakeholders throughout the Great Barrier Reef that might be very spatially, kind of spatially explicit. They care about their local area, and using those layers of complexity to kind of build in a plan for where we might do these restoration activities. I've also done some work with Alex Schroers from the Australian Antarctic Division and Justine Shaw, who I would say most of you would know, working on another type of spatial problem, which is eradicating invasive species from islands. So again, it's where should we do things if we have one bucket of money, not necessarily always just where should we put protected areas, and adds these kind of other aspects of complexity. And spatial prioritization in Antarctica is complex and is going to continue to be really complex because we have this kind of difficult landscape that we're looking at down here, decision-making wise. We might have things like cross-border actions. So just because we've divided Antarctica up into these wedges doesn't mean that's how the ecology or the environment thinks of Antarctica. So we may need to do things across borders. We may have widespread species in which conserving them on one of these management wedges in Antarctica isn't going to be enough or have enough impact to really change the outcomes for these widespread species. And we're also going to have these issues of the impact of what you do, what we do, maybe Australia, what we do on our wedges. The impacts are going to depend on our neighbours' actions. So what other people decide to do in the pieces of Antarctica that they have governance over can either bolster the outcomes that we're expecting to get from our actions, or really erode what we thought we were going to be able to achieve. And all of those are going to add a lot of complexity to this idea of spatial prioritization in Antarctica. One kind of more complex prioritization problem that I've been working on in a completely non-Antarctic different context is the idea of technology development. And so this is based in the Great Barrier Reef, where we desperately need to build some climate resilience into the ecosystems in the Great Barrier Reef. Along with dealing with global warming, we also need to build climate resilience in what we've already got there, so we don't continue to incur losses. But we don't really have the technologies that we need to be able to build that resilience. And so what we're hearing a lot of conversation about at the moment, and a lot of kind of big funding amounts kicking around, is what technology should we be spending a lot of money and time to develop with the goals of kind of doing what we don't already know how to do, which is building that climate resilience. And so my question is, how should we be thinking about, if instead of prioritizing spatially or prioritizing protected areas, we're prioritizing between these different technologies. We need to make choices now in this world where we don't really know how these technologies are going to turn out. We're kind of flying a little bit blind here. And so we're going to lean on the idea of prioritizing to spread risk because we have so much uncertainty. The Great Barrier Reef, it's a high risk situation. The technologies might fail and the ecosystems might degrade. And we see those same high risk situations in Antarctica as well. And so that leads us to think like maybe we should put all of our eggs in one high risk, high reward basket. All our eggs in high risk, high reward basket versus spreading them across multiple choices. But sometimes if we decide to invest, say, in like a bunch of different technologies that we don't think are necessarily incredibly risky, what we might see or what we might be blind to if we're not careful is the fact that risks can be correlated. So the failure to develop one of these technologies, or eventually maybe the failure of it to make impact in the ecosystem, it's not necessarily independent of what the other technologies might do. And so if we're thinking that we're spreading risk, in fact, what we might be doing is just lulling ourselves into a false sense of security, spreading our cash across a lot of different technologies that aren't actually buying us any kind of risk management. And so we're using an approach called modern portfolio theory, which is a structured method to prioritize risky investments. It's used frequently in financial systems to really, in a structured way, think about what it means to spread risk in these systems where we have high uncertainty and these kind of potential for high rewards or really high losses. And so I think that that type of approach will need to be thinking about these risks and these rewards and these correlations in the Antarctic system as well. So the other thing that I think will be useful that we're learning from this Great Barrier Reef problem that's very useful for Antarctica is the fact that when we have multiple decision makers, we can have what I'm thinking of as disconnected control. When we are just choosing where to put protected areas, it's one decision that one person is making or one entity is making, and you decide where to put these protected areas. And maybe your plans are eroded a little bit, as Michael alluded to. But in a more complex environment, we might make a decision, an initial decision, but someone else eventually will enact it. And so it really separates out like funding decisions or initial decisions from what ends up happening on the ground. And so, for example, in the Great Barrier Reef problem, we can plan what technology we invest in now and might be available in 10 years, but we can't plan how it's going to be rolled out or used or where once it's available. Or we might plan how to allocate money for protected areas, say to state governments or local governments, but we don't decide what actually is going to happen locally. And the problem is that once we're splitting our control, once we're disconnecting that control, we need to deal with the fact that other decision makers might have different objectives. They might have the exact same objectives as us, but maybe different environments that they're working in because it's the future or a different place, or different pieces of information, different knowledge of the system. So we need to be asking ourselves the questions, in this world of disconnected control, will their decisions change the optimality of our decisions? Should we be making our decisions differently based on what we think they might do in the future or in a different place? And how I've been formulating this is through the idea of bi-level prioritization. So instead of saying one person makes one decision, we have two layers of decisions. There's a top level decision maker, maybe they act first, maybe they allocate money to someone else, maybe it's our action in a wedge of Antarctica that then someone else will respond to. And then there's that following decision maker. And both of these decision-making entities have their own internal consistencies, they're making their own decisions, and they're not necessarily the same. They're both internally optimizing for something different. But what that first decision maker does impacts what can be achieved by that second one. And likewise, what that second actor chooses to do will impact the benefits that first decision maker might be getting. And I've been working on this problem with the National Institute for Mathematical and Biological Synthesis, a working group through that institute in the US, looking at allocating different amounts of money to counties, where those counties might then choose where to place protected areas. And in this really kind of preliminary analysis here, we see it really does impact what actions are taken and what benefits we might get out of the system. So we think about making these decisions in that top map, ignoring the fact that there is this bi-level problem. And then the second one is taking it into account. So just by accounting for it and by trying to enumerate it and understand it, it allows us to make better decisions as the top level decision makers. And of course, decision maker interactions in Antarctica are incredibly complex. And I think part of this theme will be learning how complex they are and trying to get that information into the problem. Now, all of this decision science stuff, I've only talked about prioritization really. There's a lot of other, of course, ways that we can borrow from the mathematics in this space for Antarctica. But really, just a reminder that our overarching objective is always to choose actions to improve the most from the baseline, given limited resources. And this is not something that we can do in isolation. So there's really clear, I think, collaborations and reliance on the other themes and our potential collaborations with political stakeholders as well for us to be able to make these types of decisions. Thank you. And I will now pass on to Matthew.